Hi, I'm Steve Albini, and today I'm going to talk about time aligning multiple signals from a single audio source. A common situation in the studio is that you have a microphone on an amplifier, but also are recording a direct signal from an instrument, a bass guitar or a keyboard or a synthesizer, for example. This causes an arrival time difference between the direct signal and the signal on the microphone to the recording medium. One of the reasons for that is that there is an acoustic delay inherent in the microphone recording the signal from the speaker. Got a little diagram here that I will show you. Sound travels very approximately 1 millisecond per foot. That's an extremely rough approximation, and it varies with humidity, temperature, altitude, local air pressure, a lot of things. But as a rule of thumb, approximately 1 millisecond per foot. So if you have a sound source coming out of a loudspeaker and there's any physical distance between the loudspeaker and the microphone, even a matter of inches, then there will be an acoustic delay in the arrival of that sound at the microphone. If that signal is also being recorded as a direct signal, then there is an imperceptible or essentially zero delay for the signal that's being recorded off of the direct signal. So the time difference between those two creates a phase difference in the two signals if you were to try to combine them. And the phase difference can cause cancellation of some frequencies, a thinning out of the bass sound, and a comb filtering effect, which can be unpleasant. Tell me when I can move. Oh, you're good. Okay, I want to show you a technique you can use to compensate for that arrival time difference by delaying the direct signal. The sound source for this example is going to be this synthesizer. This synthesizer is going through a direct box directly to the desk. It's also going through an amplifier, and that amplifier has a microphone on it, which is also plugged into the desk. The direct signal is getting to the desk from the synthesizer almost immediately. Not quite speed of light, but very close to the speed of light, a significant fraction of the speed of light. But that signal's getting to this amplifier, and it has to make its way through a pretty elaborate system before it finally gets to this microphone. It has to go through the input circuitry of this amplifier, which has a time constant.
And then the preamplifier has to get the signal to the power amplifier section, which then has to modulate the power supply through the output transformer, which then needs to couple the primary and secondary windings to the output cable, which goes to the loudspeaker, which then gets its voice coil energized. And then the voice coil then drives the speaker cone inside its magnetic gap, and the compliance of the cone needs to move the air that's in front of it. That air pressurizes, and that pressure wave travels through the physical distance between the loudspeaker and microphone. Then the microphone diaphragm needs to move and make its way through another transformer, and then down the cable to the capacitors. Then you get the microphone to amplifier.
It's a wonder it works at all. Every system is different. Every amplifier is different, and every physical installation is different. So this cumulative delay of all of these time constants can be anything from less than a millisecond to several milliseconds. And if there are effects pedals in line, those effects can also affect the latency. The arrival time difference is audible, but I can also visually show you the arrival time difference on the oscilloscope by tracking the two waveforms against each other. When I play notes on the synthesizer, you can see them displayed on the oscilloscope. The bottom trace on the oscilloscope is the direct signal from the synthesizer, and the top trace on the oscilloscope is the microphone signal on the amplifier. When I play these notes, you'll see that the waveforms don't line up. That is, the peaks and valleys will be in different locations on the timeline. And in extreme examples, they can be almost completely out of phase with each other. Well, that sucked. So I'd like to correct the discrepancy between those two signals by inserting a delay into the direct signal path. Now, the delays that you're going to use for this kind of correction are going to be very short, sometimes less than 1 millisecond. And it's important to have adjustability in the microsecond range. I recommend using an analog delay that's a studio quality analog delay, or a digital device that allows adjustment in the microsecond range. Here at Electrical Audio, we have some delays that were made for us by the Eventide company that are adjustable in the single microsecond range. So you'll need to use a delay of this type, or an analog delay, or what's called an all-pass delay, all-pass filter. So this is the signal with the delay bypassed. I'm going to engage the delay, and I'm going to scroll it until the waveforms come into very good alignment. You should be able to see the waveforms moving one against the other here. I'm now satisfied with that. I feel like the waveforms are all in very good alignment and the sound quality is very good as well. So the total alignment delay that we needed to use to compensate for the acoustic delay between the microphone and the loudspeaker and the mechanical system of the loudspeaker and its compliance ended up being 774 microseconds. That's a significant delay. But the precision of the delay allowed me to get the waveforms into very good alignment. The audible effect of this is that the low frequencies are better supported because there's less phase cancellation, but you should also hear a cleaner, less comb-filtered effect on the high frequencies as well. Another common scenario is to have two microphones on a single sound source, say a guitar cabinet. You might have two microphones with different sound qualities, or you might want to create a stereo image from using two microphones that respond slightly differently. Those two microphones, no matter how carefully you position them, are going to have some slight difference in arrival time between the loudspeaker and the microphone. And that arrival time difference can cause phase cancellation, which can muddy the sound quality. I have an oscilloscope set up here in what's called the Lissajous pattern. And the Lissajous pattern is a display that shows you the phase relationship of two signals. In this case, I have one microphone on the vertical axis and another one on the horizontal axis. And this dot will trace a squiggle that shows the phase relationship of the two microphones. So let's go downstairs and I will set these microphones up on the cabinet. So these are the microphones that I've got up on the amplifier. This is an old Rca Ribbon microphone, which had its cable replaced by our technician Greg Norman. And when he did that, he ensured that it followed the pin 2 hot convention of modern American microphones. That is, a positive air movement in front of that ribbon will create a positive voltage on pin 2 of the output connector. That's standard for almost all microphones, but there are a few oddball microphones and a few very old microphones where that's not true. So it's always worthwhile to check to see if the microphones you're using observe the pin 2, pin 3 convention. This microphone is a Russian condenser microphone, and I suspect that it's pin 3 hot and not pin 2 hot, but we'll confirm that when we listen to it upstairs. Playing guitar for us is John Sanpaulo, America's top-liked guy. He has a fucked up knee, so he can't leave. Let's go see if he can play guitar. All right, so let's take a listen to those microphones and see if we have any problems. John, can you play for me for a moment? Okay, I can hear that there's a significant phase difference between the two microphones, and it's so extreme, I'm pretty sure one of the microphones is of opposite polarity than the other. You can see that this ellipse is quite wide, and it's actually working in an anti-phase direction, that is, in the direction opposite of what it would be if it were a mono signal. So I'm going to try flipping the polarity of the microphone that I think is the culprit and see if it brings it more into alignment. Well, that sounds better to me, and I can see verified on the oscilloscope that I have brought the two signals more into alignment. So my hunch about the polarity of that microphone was correct. So from looking at the display, I can't tell which of the microphones is too close and which is too far. But by listening to the two microphones in stereo, I can hear that the image is pulling very slightly toward the side of the condenser microphone. That means my ears can detect an earlier arrival of that signal. And that means that the condenser microphone, relative to the ribbon microphone, is too close. Thanks, John. Let's go down and see if we can correct that. I could tell from listening that this microphone was a little bit farther away from the cabinet than this microphone. So I'm going to move this one in a little bit. It wasn't a drastic difference, but it was probably enough that I could measure the difference. So I'm going to use my hands to see if I can estimate how much I need to move the microphone. And it appears that this microphone needs to move about an inch, inch and a half closer to the speaker. All right, let's go see what it sounds like. Let's see how it sounds with that adjustment. John, can you play the guitar for me for a moment? So that sounds better to me, and I can see from the Lysergy display that the ellipse has narrowed considerably, which means the microphones are more closely in alignment. There are, however, still some curlicues that indicate that there is some phase cancellation going on at certain frequencies. And when I listen in stereo, it sounds to my ear like the ribbon microphone is now slightly closer than the condenser microphone. So I want to make it another small adjustment. I think we can do better than that. I could tell from listening that this microphone needs to be a tiny bit closer, but not very much. So rather than try to move the stand, I'm just going to slide it in the mic clip a fraction of an inch. That should be enough. Let's go see. So let's see what that adjustment sounds like. John, can you play the guitar for me, please? So you can see here that the two signals are in very close alignment, making a very narrow ellipse, but there is still some difference between the two microphones that will allow us to hear the stereo image I was describing. You should never be afraid to experiment with things like trying multiple microphones. Diagnostic tools like the oscilloscope and your own ears should guide you in moving and correcting placement errors.